We've discussed the image of why a DC offset reduction or mismatch reduction through the trimming technique for any differential circuit block. But the trimming is an offline calibration. As we discovered, even though the one-point trim could reduce the offset near to zero, the variation of the supply voltage or temperature after trimming may raise the input offset again, and you might need a more precise calibration. In addition, adding multi-point trim will mitigate the variability after trimming, but you might not tolerate either the cost or complexity. What can we do? Correct. Instead of the offline or static cancellation for the offset, we should apply the dynamic or background offset cancellation to remove any mismatch during the environment change, like the temperature or supply voltage drift. Unlike the trimming, to apply the offset cancellation dynamically, we must come up with a way of measuring the offset and remove it completely by knowing the offset value from the major offset. Since the offset could be removed almost to zero from time to time, people also call it the auto-zeroing technique, which we will cover in this video, and you will also know why it's called auto-zero. Alright, let's start with how to implement the auto-zeroing technique with a simple cartoon here. First, you might remember a unigame buffer configuration by using an ideal op-amp or OTA as shown here from the Microelectronics 101 class. Second, for a real amplifier, the ideal op-amp or OTA model is still valid by pulling out the real amplifier's input offset to the ideal OTA's input. Third, since the input signal is replaced by the input offset, the unigame buffer may only pass the input offset directly to the output and store on the CX at the negative input. Please note, there is no input signal connected in this major phase. If you do, you cannot differentiate the input signal and input offset properly. After understanding the offset major phase, how do we cancel it? Think about the normal operation images for 5 seconds. Bingo! Just simply apply the normal operation during the cancellation phase, which implies the auto-zeroing the offset. But how does that work during the cancellation phase? Remember, the intrinsic input offset was assumed at the positive input and then got measured and stored at the negative input. Therefore, through the normal differential operation, the same input offset is shown at both sides to be a common mode voltage and must be cancelled to be zero at the output. On the other hand, the input signal only shows up in this cancellation phase, but not in the major phase. Therefore, the differential signal will be amplified properly, and that explains why both normal amplification phase and cancellation phase can work at the same time. But there's one subtlety here. Think about the two-phase images for 5 seconds. Correct. To separate two phases of offset measured and signal amplification, we must add a switch and control it during the proper time as shown here, such that each configuration can be made. First, for the offset measure phase, the switches S2 and S3 are closed, but S1 is opened to isolate the input signal. Then, the intrinsic input offset is stored at the CX. Second, for the amplification phase, the switches S2 and S3 are opened, but S1 is caused to pass the input signal. Then the input differential signal is amplified, while the intrinsic input offset is cancelled through the differential configuration. Please be advised that the switch's configuration to do the auto-zeroing at the input offset was just one implementation. Do you see any implementation here to reduce the accuracy of the offset cancellation? Think about the input images for 5 seconds. Right. First, the unit gain buffer may not be exactly 1 due to the finite amplifier gain. Therefore, the sampled or the major offset at the negative input will not be exactly the same as the intrinsic input offset at the positive input. Quantitatively, the input residual offset is nearly the intrinsic input offset divided by the amplifier gain. Second, the switch is not perfect during the on and off state. Therefore, the on register of the switch will either add the thermal noise KT(C) or voltage drop to degrade the voltage accuracy at the amplifier's negative node. During the on state to the off state of the switch, either the switch's charge injection or the current feed-through will further degrade the voltage accuracy at the amplifier's negative node. The switch impairments mentioned above will certainly add extra residual offset. How can we improve it? Think about the input-output images for 5 seconds. Yes, we can do the input auto-zeroing, which means we should be able to do the output auto-zeroing as well. The idea is exactly the same as follows. First, show the input differential nodes without input signals, but get the output offset stored at the differential output, closing the output switches. Second, it switches to the input differential signals and open the output switches in the amplification phases, such that the signal is amplified and we cancel the offset at the output. Unfortunately, someone may notice that the output switches still have the on resistors KT(C) noise and charge with the clock feed-through at the output. Interestingly, notice the residual offset is at the output, not the input. Therefore, the input residual offset from the switches will be divided by the amplifier's gain, which could be at least 10, and the input offset is reduced reasonably without adding too much capacitance for the KT(C) noise or causing the switch design challenge too much. But there's still a subtlety here. Think about the gain images for 5 seconds. Perfect. The previous analysis or assumption is that the output is still within the dynamic range. For example, if the amplifier's gain is a lot, like 10,000 at a 1.8 volt supply, then what happens at the output if you apply a 1 volt input in an open loop configuration? 10 volt from 1 volt times 10,000? Correct? Of course not. That output will saturate or clip to 1.8 volt, since that's the maximum supply voltage you can get. Hopefully, this may show you a simple idea of the subtlety of a limited maximum gain for the output of auto-zeroing. But what's the maximum gain you can have? Right, that depends on the input dynamic range or swing. You will need to determine the output level under the supply voltage without clipping. Hopefully, this image can help you determine your own specification according to your usage. Since there are lots of different auto-zeroing technology according to your system requirement or usage, Probably we don't need to show all the topology here. Instead, we could revisit the advantage of the auto-zeroing one more time. First, the dynamic auto-zeroing can cancel the input offset over time. Therefore, the residual offset would be smaller than the trimming over PVT variation, which is one natural advantage of the dynamic mismatch cancellation. Another one is the good stability over time in the input common mode and supply voltage variation. Since the input mismatch was cancelled continuously, both the input common mode rejection ratio (CMR) and power supply rejection ratio (PSR) are excellent. Lastly, there's no additional cost or on-chip trimming memory elements needed. Here are the summarized images of why we need a dynamic offset or mismatch cancellation with the auto-zeroing technique. Even though 1-point trim could reduce the offset to tens of microvolts level, the variation of supply voltage or temperature after the trimming may raise the input offset up to hundreds of microvolt level. In addition, adding multi-point trim could reduce the variability after trimming, but you might not tolerate either the cost or the capacity. Therefore, instead of the offline or static cancellation for the mismatch, we should apply the dynamic or background offset cancellation to remove any mismatch during the environment change like the temperature or supply voltage drift. The intuitive concept is straightforward. To measure the intrinsic input offset and then apply the same offset to cancel the intrinsic input offset, which is the so-called auto-zeroing offset cancellation technique. But to separate both phases of offset measurement and signal amplification, we must add a switch and control it during a proper timing, as shown here, such that each configuration can be made. First, during the offset measure phase, the intrinsic input offset is stored at the CX. Second, during the amplification phase, we amplify the input differential signal while we cancel the intrinsic input offset through the differential configuration. Please be advised that there are lots of different auto-zeroing topologies according to your system requirements or usages. Let's summarize the auto-zeroing advantages. First, the dynamic auto-zeroing can cancel the input offset continuously. Therefore, the residual offset could be down to tens of microvolts easily. Second, both CMR and PSR are excellent over time owing to the little residual mismatch over time. Lastly, there's no additional cost or on-chip trimming memory elements needed here. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefit from it.